Hello, my name is Zibulevsky. This is the first lecture of our course, Algorithms for Nonlinear Optimization, Spring 2009. In our course we will consider two types of problems. First, unconstrained optimization problems. Find minimum of a function of several variables. Minimum f of x such that x is a n-dimensional vector in Rn. So f is a function from Rn to R, and we will consider optimization of only continuous functions. Continuous. And a large part of our course will be dedicated to smooth differentiable functions. But at some point we also will consider non-smooth functions. And other topic is optimization with constraints. Optimization with constraints. Find minimum of f of x. Again, x is a vector from Rn. But additionally, we will require that some functional equalities or inequalities should be satisfied which restrict area of feasible values of our vector x. So we write in this way, subject to some functions gi of x say less or equal 0, I from 1 say to m, and possibly some other functions hi of x or hj of x equal to 0, j from 1 to l. This kind of constraints we call inequality constraint, and this equality constraint. And in our course for both unconstrained and constrained optimization problems, we will consider how can we know whether point we have is already optimal solution, which is called optimality conditions. And the major part of our course will be dedicated to iterative algorithms which approach this approximately or in limit this optimal point. Why we are interested in this? Because in many cases, in many very practical and very important cases, it is impossible to write optimal solution in analytic way. So This was first part, and second, numerical iterative methods. To achieve optimal, to approach, to approximate in limit optimal solution. Sometimes if you are lucky in finite number of iterations you get to it. Okay. Now we will consider several examples of unconstrained and constrained optimization problem. Let's start with unconstrained. And the first example will be parametric regression. So, what kind of problem we try to solve? Suppose I have some experimental data where x are some argument, value of argument, and y my measurements. Say there are a number of experimental points, and I suspect that the actual physical process is described, for example, by quadratic dependence of y from x, but my measurements are noisy, and I will try to obtain a quadratic parabola which goes as close as possible to my measurements. How can I write this formally? I am given a set of pairs xi and yi, xi, yi, I from 1 to, for example, capital M. I need to find in my case quadratic functions. Quadratic function f of x, and the coefficients of this quadratic function I will denote as w. So even I will write it explicitly as w0 plus w1x plus w2 x squared. And how can I pose my problem as optimization problem? I will write the following error expression. Sum of errors, sum over points I from 1 to m. Difference between my model f of xi, experimental point, and w, minus my measurement yi, and say all this squared. I'd like to minimize mean squared error, despite in many other applications instead of square, here may be different penalties for error value. And I like to minimize this expression over my parameters minimum over W. W is a vector of W 0, 1 and 2. And this is a particular case of quadratic function. Again, I wrote my old quadratic function here, but in more general case, instead of having constant, linear and pure quadratic function, we can have some general functions of x, and say we like to approximate our unknown function f of x as sum of as weighted sum of known functions phi k of x, and in this case this is called linear regression problem. Despite those functions are nonlinear functions of x, but our optimization problem, our function is a linear function of w, and optimization problem is a pure quadratic problem with respect to w, and often even may be solved analytically, as we will see in our course in the future. But also there are very important cases when our approximation model is nonlinear with respect to w, and this will bring us to so-called nonlinear regression. And important case of nonlinear regression are so-called neural networks. Let me show you this example. It's very interesting and rather important in many applications, like function approximation, prediction, pattern recognition to recognize handwritten text, and many others. So, what is a neural network? Suppose that we want to approximate a function of several variables. In this case, x is a vector, and here x1 till xn are entries of this vector. And for example, b is some constant. What one single neuron does, it summarizes, computes sum of entries x, but not just sum, but sum with weights. So x1 multiplied by some w1, x2 by some w2, xn by wn, and all this plus b, and then it takes some nonlinear function of obtained result. I will write it as phi, some function phi, and this will give me output y of a single neuron. So all inside everything this we call as a neuron, and often it's symbolically is shown as one circle. So again is our x, and here are inputs, and here are weights, wi and b, and output y. And this nonlinear function, rather typically, it function looking in the way as arctangents looks, and it's called sigmoid, phi of one variable, say t, and it's called sigmoid. There are many mathematical expressions, many different mathematical expressions for such type of functions. And also I should say that sigmoid is a very popular choice, but there are also other choices. And if you like to write formally, we can say that our output y is w transpose x. All w's we can put as a vector, w transpose x plus b. And from this we took a nonlinear function phi. And having a neuron as a basic element, one can build a network of such neurons. And actually this network is a very powerful approximator of general functions of many variables. There are even theorems that in limit, when number of new neurons is increasing, it may approximate any smooth nonlinear function to any given accuracy. So how it usually looks, again, let x is our vector, and here are entries of x, x1, xn, and we will even put, let us put several neurons. How can I denote them? Even I, in general form, will write this as phi j. So, and x, for x I will give index I, xi. And the network may be even fully connected, but it not necessary. But for example, all our x is connected to first neuron with some weights. Say this is w11 and this is w21, and so on. And for example, also every input connected to the second neuron. For example, this is w22, and so on. And then outputs of the first layer of neurons maybe serve as inputs of the second layer, and so on. But we will here consider example of limited, simple, relatively simple neural network, where second layer will be just linear elements which compute a weighted sum of the inputs, and we will denote them as dots, say several dots, and okay, outputs of neurons go here and here and so on. And let denote us those weights by different letter, for example, as V, J, K, And this function, as I told in the example which we will consider, it will be linear, but in general I will write this as psi k. And okay, and then some other coefficients, say ck, and this will be output of all the network Y. I also forgot to add constant entries which we called B. So it's B1, B2, and so on. B in some index. I will find later the letter for number of neurons. And okay, let me denote the input of every nonlinear function, which is sum of weighted x's plus b, as u. And then say u1 will be input of nonlinearity here, u2 here, and so on. And you can see yourself that we can write it in matrix form, that the vector of all inputs of nonlinearities is w transpose x plus b. So W is the matrix with those entries, weights of first layer of neurons. And then we can denote a function of vector as a vector with entries of function of every element. Say, I can write formally phi of u such a vector. This will be my definition of my local concrete vector function. So it's phi 1. Let's forget for a moment about indexes with phi. Phi of u1, phi of u2, and so on. And having this notation, I can very compactly express what neural network does. Let me write, and then you will check me. So again, I have this W transpose X plus B. This is my U. Then I apply to it nonlinear function. This is actually vector. So I apply this vector elements wise function phi. Then I multiply it by matrix V transpose. And then I apply a similar function psi to this expression. Again, what is inside here is a vector, because it's matrix multiplied by some vector here, and here maybe probably some other bias, but I don't write here in this particular case. And then we multiply by transpose of vector C. And this is our function of neural network. So this is our function of x. X is input, and all these parameters. What are parameters? Matrix W, matrix V, and matrix W, vector B, matrix V, and vector C. And this is my function. And now with this function in hand, I can try to approximate any set of data points I have, for example, from experimental data. So, for example, let me remove this. Again, I have a set of my data points, say xi, yi, where say I from 1 to capital M. For every example, x is a vector. For every I, x is a vector, and y, for example, is a scalar. And I like to approximate, to find such a function, such a neural network, to find actually weights of this network. That for given set of data points, my function will approximate y values which I measured. So how can I write it in general? I will write as optimization problem. Minimize over a set of my parameters w, b, v, and c. Sum over my experimental, sometimes it's called training examples, I from 1 to m. For example, square error, square difference between my function f of xi with these parameters w, b, v, and c minus measured y's, yi. Squared. And this is a very nonlinear optimization problem with respect to all those parameters, except of last one. Yes, with respect to c, the problem is linear, but with respect to other parameters, it's strongly non-linear. But the methods we will learn in the course are able to attack this problem as well. Our next example will come from a completely different area from economics, and this will be an example of optimization problem with constraints. And the problem is called resource assignment. And we will consider some concrete example. For example, we have a number of power stations and number of customers, and there will be there is some limits on the power of each station and the known demand of customers, and there is some cost for transportation of electricity from every station to every customer, and we like to optimize overall cost over network to plan how many electricity from every station to every customer should go. So let's write this formally. So we have m capital power stations, and say S in index m is maximal power of station m, max power of station m, and on the other hand we have customers, n capital customers, and Cn is demand of customer n. Okay, now what we have between them, we have known cost PMN PMN. This is a transportation cost of electricity unit, of unit of electricity, of unit of electricity from station M to customer N. And we want to find amount of electricity. Find matrix of unknowns with entries x, m, n. Amount of electricity. Which we want to transport from again from station M to customer N. Okay, so let us write optimization problem. We like to minimize total cost. What is total cost? This is sum of PMN multiplied by XMN. And we want to minimize it over X. Capital X, I will denote matrix with all entries, XMN. And we have constraints. I will write subject to. First constraint is every power station cannot produce more than SM. So sum of all customers of this station, sum of n from 1 to capital N, XMN less than equal to SM. This is for station M. And of course this should be right for every station M from 1 to capital M. Another constraint, I should be sure that I have a space on the blackboard. Okay. Let's try to manage. Maybe I will remove here. So another constraint, I continue, instead of writing it compactly, I need to get to the top, to my whiteboard. Customer N should get the amount he demanded. So sum over all stations, sum just a second, sum M, M is equal 1 to capital M, X M N is should be equal to Cn. Cn is demand of customer N. Again for all N, from 1 to capital N. And also by physical considerations, despite that this is not so in modern system, we think that electricity goes in one direction only from station to customers. Now we know that customers are able to produce their own electricity by sun or by wind and so on. But this is an example from old handbook, and they didn't have this yet. Didn't consider this possibility yet, and that's why they wrote xmn greater equal to 0. Okay, so this is an optimization problem with constraints, with inequality constraints and equality constraints, and put attention that in our decision variables x, also objective function, also constraints are linear, and that's why this problem is called linear programming problem. Linear program. Linear program or linear programming problem. Two terms are used.